Perfect. So, hello to everybody. It's a pleasure to host Eduardo Calo. Eduardo holds a bachelor degree in Asian Studies from La Sapienza, so quite close to Pi School and Pi Campus, and then a master degree in natural language processing from the Université de Lorraine. Currently, he's pushing a PhD in natural language processing group at Utrecht University in the Netherlands. His research focuses on natural language generation and specifically on logic to text generation, which is a subfield of natural language generation that aims to generate intelligible text explaining the meaning of logical formula. So very, very peculiar sector. I want also to mention that Eduardo is a friend of mine and was also a colleague of mine when we were working together on the Samsung Bixby project. And in today's talk, Eduardo will introduce natural language generation and illustrate its key challenges with a focus, obviously, on logic to text generation, which is his main expertise at the moment. So he will present also some results from his research and maybe also an interactive demo to all of us. So welcome again, Edu, and we can start.
Thank you so much for the really kind introduction. And yeah, it's a pleasure to be here and presenting my work and results to all of you. And yeah, so the title of my talk is At the Crossroads Between Logic, Language, and Generation, which is exactly the topic on which I'm working on at the moment for my PhD. And I'm also part of the NL4X AI framework, which is a European framework which comprises 11 PhD students all across Europe. And thanks to this, we also have some exchanges and visiting in other universities, which is very nice. And so yes, let's start with the talk. So first of all, I will give an overview of the presentation that I will give. So I will start with an introduction of my topic. I will list the motivations, the challenges, the methodologies, and the applications that my work has. Then I will focus on two main challenges of my topic, which is how to properly evaluate the output text that these, let's say, algorithms in general can generate, and how modifying and manipulating the input formulas, the impact that manipulating input formulas has on the resulting text, which is generated by these algorithms. These are the two main issues that in this 1.5 years of my PhD I've focused on. So I will also present some results and some papers that I've published that are under review. And then I will mention some future work and path that can be explored and that I have already started exploring. And then I will end up with an interactive demo, which unfortunately didn't have time to Dockerize it, so you cannot use it, but I can use it, and we can play together, let's say. So yes, let's start with the introduction. So in general, what let's say the general area of the topic in which I'm specialized is meaning representation or semantics or concept to text generation. So given a formal representation that somehow to some degree captures the meaning of linguistic expressions, then you have algorithms that generate some informal, between quotes, natural language text. I say between quotes because natural languages are not totally informal. There is some structure, but I wanted to highlight the difference between formal languages, which have some specific structure, some specific syntax and semantics, and natural language, which is much more ambiguous, complicated, with different factors that can play a role. So all of these all of the things that you can see on the left are meaning representations. if you ever heard about abstract meaning representation, these DRSs, but also mathematics and code can be considered as a concept or semantics. And my focus is on logic specifically. So this is the problem statement that is the focus of my PhD. So given the formula that you can see here on the top, this is a formalism called the first order logic. Probably some of you are familiar with this. My aim is to create algorithms that can generate these text, which have the same the original formula, which means that they can explain the original formula that you have as an input. Of course, algorithms can generate several different realizations of the same formula, but the most important thing is that these generations need to be faithful, so need to have the same meaning of the original formula. And the differences between the text that the algorithms generate is that some of them can be more fluent, less fluent, comprehensible, less comprehensible. So this is the general problem statement of my PhD. So why do we do this? So first of all, this subfield of natural language generation is overlooked with respect to other tasks. For example, data to text or table to text, or I don't know, summarization or other natural language generation tasks. And most importantly, NLP models in general still struggle with the logically rich text. Here, I just put 3 references, but there is like a huge body of literature that shows that these models are still not do not perform well with these logically rich text. So the first here relates to the negation and BERT models. This other one with the confusion that models make between conjunction and conjunction or. And this last one was presented at a workshop at NLP last year, and it's related to natural language inferences with the logically rich text. So there is a lot of work to be done. That's the point. The key questions and challenges of my topic are the biggest ones, of course, are how do we build and how do we evaluate a logic to text generation system? So building, of course, goes to the input side of things. So there is a long-standing problem, which is called the problem of logical form equivalence, which was formalized by Schieber in 1993, and which states that since there are infinitely many equivalents to an input logical formula, how do we choose the best formula as input? So to give you a concrete example, imagine this formula here. Imagine that there are infinitely many logically equivalent formulas, which means that all these infinite formulas have the same meaning as this one. So how do we choose the best input to give as a system like this to generate text from that input? So this is the first big challenge that we can encounter when working with logic to text generation. The second one is the output. How do we devise proper evaluation methodologies to evaluate the quality of the generated text? And here, of course, how do you automatically evaluate it? How do you use humans to evaluate it? But most importantly, which are the evaluation dimensions that you want to take a look at, search for in the generated text? So for now, in the works that I've done so far, we focused on the first 3. Faithfulness, which is the output text should have the same meaning and convey the same information as the original input formula. Comprehensibility, the text should be comprehensible to humans. And the third one is fluency. Of course, the text should be fluent based on the grammar and morphology of the language at hand. Also, ambiguity could play a role. I haven't taken a look at it so far, but I'm working on it at the moment because we saw that it's a big issue in this field. But more on this later. So methodologies. Well, of course, there are these 2 big paradigms in natural language processing: rule-based and neural approaches, and of course, both of them have pros and cons. So I decided to take 5 points and comparing rule-based and neural approaches. So as far as faithfulness is concerned, we know that rule-based approaches, since they are manually crafted, you can ensure the fact that the generated text is always faithful to the original formula. But with neural approaches, when there is some sort of learning involved, this is not ensured anymore. So this is the first big difference between the two. Then fluency, we know that large language models now are very good at generating really fluent text. While with the rule-based approaches, the structures and the grammatical and morphosyntactic structures that you can implement in these systems is very limited. So you know that with large language models, you get text which is more fluent. But we also know, as I said before, that they can spit out garbage. So text which is not faithful to the original input. Coverage, similar to fluency, we know that with the rule-based methods, we are limited to some specific domains, some specific lexicon, some specific part of the grammar of a language. While with neural, you can give them whatever you want, and probably you will get some results. The same goes for data. With rule-based methods, you don't need much data. You just need some smallish corpus to provide some examples to these systems, while neural approaches need a lot of data. And this goes along with a big problem that in logic-to-text generation, we actually do not have many of these data sets. So it's very difficult to find data sets which are parallel with the formulas and text. How do we encode the formulas? So with rule-based methods, of course, it's just symbolic. So you can decide to, I don't know, part of the formula corresponds some structure and things like this. While with neural approaches, this is a really big open question. We don't know. There are some works in the literature which have tried to consider symbols in the formulas like embeddings, like word embeddings, let's say. Others which have tried graph neural networks, because formulas can be represented with graphs. So yeah, this is a really open question that we don't know how to solve yet. So what are the applications of this whole enterprise, let's say? So first of all, there are some explainable artificial intelligence methodologies that use logical formulas as an input to explain black box models. So one of the applications of our of logic-to-text generation in general could be to translate these logical formula outputs into text, which is comprehensible also for people who are not, let's say, accustomed to logical formalisms. The second application could be tutoring systems for logic teaching. So this logic-to-text generation enterprise can be implemented into systems that can help both students and teachers to study and teach logic. Okay, so I will turn to the first main challenge and the first thing that I focused on during my PhD, which is how do we evaluate the output text that are generated by whatever system. So this is my first publication, which I presented last year in December at a workshop at IMNLP, and it's a collaboration with my supervisors and a master's student that we co-supervised. And yes, so the main motivation of this work was that all the relevant literature in logic-to-text generation that I summarized in this table do not actually properly evaluate the generated text. So as you can see here, most of the systems do not even attempt to automatic evaluation or to a human evaluation, while some others, especially the most, let's say the newer ones, try to evaluate the generated text from formulas in some ways, both automatic and in a human fashion, but none of them have a, let's say, comprehensive evaluation. So that was the focus of this work. So we started from a model which was presented in the literature, Ranta 2011. And this system basically translates a string from one language to another in 3 steps. It takes an input formula as input, then it parses the input formula as an abstract syntax tree, then it optimizes the tree with some natural language generation techniques, some such as flattening, aggregation. I don't know if you're familiar with these terms. And then takes this simplified syntax tree and linearizes it in natural language, in this case in English. So from this input formula, you have the output text, every number is even or odd. This is how the model which we found in the literature works. But there is no attempt of any evaluation of this system whatsoever in the original paper. So what we did was we took some data, both manually crafted, so a corpus of parallel formulas, a parallel corpus with formulas and text, and formulas which are randomly generated to cover all the possible space of formulas. So both easy, both difficult, long, short, to see how this model actually performs with a large variety of formulas. So how did we assess this system? So we asked human evaluators to assess faithfulness, understandability, comprehensibility, and fluency. And most importantly, we asked them, given a formula and the translation from the Ranta system, to give a better translation. Based on the results of this translation quality assessment, so the summary of the results, you can see them on the table, and the formulas from the manually crafted corpus are more comprehensible and fluent than the ones which are randomly generated, which was expected. But the most important thing of these results are the results which we got from the suggestions of the better translations that we received from the evaluators, because we could categorize all the translations, the better translations that we got into 3 different areas. So the first one is syntactic optimizations. So the translations which were given by the system could be improved by working a little bit more on the syntax of the generated text. So for example, here you can see that this very clumsy linguistic structure, it is not the case that can be easily injected into the sentence directly using a inward negation, no. The second, let's say, group of improvements could be done at the logic level. For example, here you have a double negation, which you know that can be removed without changing the meaning of the formula. So something like it is not the case that, it is not the case that, blah, 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 could be just realized as A is medium, removing all these clumsy and complicated linguistic structures that make the text less comprehensible and fluent. While the last one is more complicated because it's at logical linguistic level, and we call them linguistic paraphrasing. And this is an example, but I have a lot of them in the paper. You can see all the different paraphrases that we received as suggestions. And here, instead of repeating let's say the mirroring of A is to the left of D or D is to the left of A, you can use the linguistic periphrastic the other way around. So based on these results, we operationalized the definition of well-behavedness. And we actually said that formulas which contain a bucket quantification, which is basically these things, so basically a variable which is not then expressed in the formula, which contains double negation, nested implication, and more than 8 connectives, are not very well suitable as an input for being translated into natural language text. Taking all these into account, we enhanced the original system presented in Randa 2011 by implementing all the logical equivalence rules that you can see here on the left table inside the system. So just to give an overview, all the formulas that you see here, so for example, this one, left-hand side and right-hand side, are equivalent. So all the things that you see here are logically equivalent. The things that you see on the left-hand side and right-hand side are equivalent. So what we did was taking all these rules and injecting them into the system. How it works? So given an input formula, all the possible logical equivalence rules are applied to the input formula up to a certain depth. As you can see here, you take this input, this formula as input, then you apply 1, 2, 3, 4 rules, and you get these formulas which are equivalent, logically equivalent to the input. And then you go on until a certain depth of the tree. We decided to set it experimentally at 5, but this number can be, of course, changed. Then what we did is generating all the formulas into natural language text, and the best one was, we selected the best one based on the length of the natural language text that we generated. So basically, the shortest one in number of words was selected as the best translation overall given this input formula. In this case, the better translation would be 2 is even. Okay, instead of for all x, it is not the case that 2 is even. Then, how we evaluated this system? So we compared the 3 systems, a baseline which generates near literal translations of the formula, the original system presented in Randa 2011, and Lola, our system. And we focus on 2 dimensions, comprehensibility and fluency. So the automatic evaluation, what we did was comparing the references of the Great Grander Corpus that I mentioned before with the formulas translated into English by the 3 systems that we are comparing. So we got very interesting results, which were also not quite expected, because imagine that the formulas, so the text that we are comparing, so the translations and the golden reference that we have in the parallel corpus are actually all of them paraphrases, because the generated text explain the formulas, while the reference is of course a reference that explains the formulas. So you would expect that semantic-based metrics, the results of semantic-based metrics should be comparable across systems, but this is not what happens. This only happens slightly when we use the BERT score as an evaluation metric, whereas with SBERT and SMS and WMD, this doesn't happen. While as far as n-gram metrics based is concerned, we get a substantial variance in the results. And this is very much expected, because as you can imagine, the realized text using the 3 systems are actually very different. So having a variance in the results in n-gram based metrics, that's what we actually want. And as you can see here, Lola actually outperforms all the other systems, which implies that it generates text which are more similar to the ground truth reference, which should be an indication that the texts are more fluent and comprehensible. But to be sure of this, we devised a human evaluation. So first of all, we devised a human evaluation based on natural language inference. So we got the output of the systems as premises, and we manually crafted the hypothesis, and human evaluators had to say if the hypothesis followed from the premise. And this natural language inference task was to evaluate the comprehensibility of the formula of the generated text. While for fluency, we decided to give evaluators a formula and the translations given by the three systems and rank the three translations based on fluency. The results of this human evaluation, you can see the one on natural language inference on the left, and you can see that Lola outperforms the other two systems, especially with the ILB8 formulas, the one that are not very well suitable for translation, because what happens is Lola first manipulates the formula and then translates it into natural language, while the other two systems do not do it. So manipulating the input helps a lot. With fluency, we get the same results. The translations for Lola are more fluent than the ones coming from the other two systems. We proceeded with a manual analysis of the results. I will just focus on two of them because I don't have time, but after that you can ask questions. So I will focus on the first one and the fourth one. So the first one here, what the metrics, the automatic metrics compare is the derealization, nothing is a cube, and the original reference, there are no cubes. You can see that these two are paraphrases. But humans give an analyzed score of 1, which means that the realization is extremely comprehensible for them, while the metric score, in this case Rouge, gives a score of 0. Because what happens with Rouge? Rouge just compares n-grams. And in this case, you can see that there is no n-gram overlap between the realization and the reference. So you can see that between the evaluation of humans and the metric, there is a huge mismatch. And the same goes here for number 4. B is larger than both A and E versus A is smaller than B and E is smaller than B. Humans consider this realization as not fluent, because of course this could be better realized as A is smaller than B, and so A and D are smaller than B, for example. So fluency was ranked quite low, while the metric score, in this case BERT score, was rated very high. And we were very surprised because, as you can see here, there are antonyms involved, which is smaller and larger. And BERT score actually captures this semantic similarity between the two antonyms. And we were quite surprised by these results. So, to conclude, the main takeaways of this work were equivalence loss help generate more comprehensible fluent text. And as you could see from the last manual analysis, there is a lack of appropriate automatic metrics to score the generated text, because basically there is no, let's say, correlation between the humans and the humans' judgments and the metric scores. While I was presenting this at EMNLP, many people, and also, of course, while we were analyzing the results, we noticed that Lola does not necessarily find the shortest logical equivalent. So I will move now to the second main challenge of my topic, in which I've worked on so far, which is how do we manipulate properly the input formulas to get a text which is more comprehensible and fluent. So this is another work that you can find already this one on archive, but it's under review to a conference. And this is something that I worked on during my internship in Barcelona at the end of last year. And this work was very much logical oriented. So I will just give a really brief and a really general overview. If you're really interested in the logic, you can take a look at the paper, but I will not explain the logic of this work with it because it's very, very deep and complicated. But I will explain the general idea of the work and of the algorithm and how we applied it in logic to text generation. So we started from the intuition that I mentioned before, which is shorter utterances should be preferred over longer ones, which is also something which is been around and has been around linguistic debate for basically forever, at least since Grice, the very famous pragmatician, which one of Grecian maxims, which is the submaxim of brevity, states that shorter utterances should be preferred over longer ones, and that useless prolixity should be avoided. This maxim could also be applied to our work, which in this case would imply that formulas which are shorter than logical equivalent, the longer one, when translated into natural language, should be preferred over a translation which comes from a formula which is longer. But what we were interested in is the shortest equivalent formula the best input to a realizer to be realized into natural language? So we devised an algorithm that ensures that always finds the shortest equivalence to a given formula. I gave an example here to clarify things. So take this formula, take this propositional formula as input, which contains 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 symbols. Symbols are predicates and connectives. When you give this formula as input to this algorithm, you receive all these outputs, which are logically equivalent to the input, which means that they have exactly the same meaning as the original input, but they are very much structurally different. And they are the most possible shortest equivalent that you can get. So in this case, all these outputs have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 symbols. You get many outputs because there are a lot of formulas which are equivalents and are the shortest possible equivalents. Given all these things, we applied this algorithm into another work that also this one is under review to another conference. And imagine that the title is self-explicative because it's shortest, always best. The role of brevity in logic to text generation. So, as I said before, we want to know if, given the shortest input, the realized text is actually more comprehensible and fluent than another text coming from a longer logical equivalent. How we experimented this? So we always got the same great grande corpus, the corpus that we used also for the other work that I explained before. We simplified, so we minimized all the propositional logic formulas in the great grande corpus using the algorithm that we developed in Barcelona. So imagine one great grander formula, several shortest equivalent. Then we realize all these shortest equivalents using the three generators that I presented before. So baseline, Ranta, and Lola. And you get several different realizations of all these formulas. So now the biggest problem is how do we choose among the pool of all these shortest equivalents, right? So to pick between all these candidates, we experimented with the 5 different selection strategies. Length in number of words, and perplexity and slur computed using BERT and GPT. If you are not familiar with slur, it's basically similar to perplexity, but it penalizes unigrams which have a higher probability in the lexicon. So here, to clarify a little bit, I put some examples coming from all the systems that after the pruning, all the systems that we have. So if you count, we have 5 selection strategies, 3 systems. And if you combine them, 5 times 3, we have 15 different systems, which is minimized baseline Berslore, which is the selection strategy, minimized Randa, the other realizer with the other selection strategy, and so on. Additionally, we also translated the original formula without any simplification with the 3 realizers. So at the end, you end up starting with 1 original input formula, you have 18 different realizations. And as you can see from this table, the realizations are extremely different, but all of these are paraphrases. All of these have the same meaning. So we started with, again, an automatic evaluation, and it was similar to the one that we did on the other paper. And what we got from this automatic evaluation is that we get a hint that formula minimization generally improves the translation. Indeed, as you can see here, the variance, the system variance, which get the minimized version of the formulas, get higher scores with respect to the ones which get the original formula as input. Additionally, we found out that slur and perplexity yield similar results as selection metrics. You see, the results are basically the same. Almost the differences are almost negligible. We were a bit surprised by this because slur for the text that we have should be better suited, but we didn't get this in the results. While the differences between semantic-based metrics, in this case BERT score and SPERT, and n-gram-based metrics, Bleometer and Rouge, corroborates the results that we got in the other paper. So semantic metrics, as you can see, they are very similar, especially BERT score. They are very similar across systems, and you get more variance in n-gram-based metrics. Which is what we expected. Again, something that we need to take care of and be very careful is the results from these semantic-based metrics need to be taken with a grain of salt, because BERT score actually has been shown that it's not very good at handling, as I showed before at the beginning with the challenges, do not actually captures very well the nuances, for example, negation or the difference between and or, which is crucial for evaluating our results. Because if BERT score messes up with an and or, the semantics of the text that we generate are completely different. So the results are what we expected, but still, there is something that we need to work on a little bit. So to understand properly the impact of formulas minimization on the translations, we went for a human evaluation. This human evaluation works like this. We gave a sentence, and we asked evaluators to rate comprehensibility and fluency on a 7-point Likert scale. And if the comprehensibility of the sentence was rated below than 4, so 1 to 3, we asked them why, for them, the sentence was not comprehensible. And we gave them 3 options plus 1 free. So ambiguity, length, and structure of the sentence. And we got very interesting results. So the results that we got are surprisingly that the difference between Lola, which Lola gets Lola, which gets the original formula, so without any manipulation at the source, but is manipulated inside the system. You remember with the tree, and the variants which get the minimized version of the formula using the algorithm that we devised in Barcelona actually do not have any statistical significance difference. So it means that as far as the formula, the input formula, is somehow manipulated, whether with rules or with an algorithm that finds the shortest, then you're good, right? Because we found no statistical difference between these groups of systems. And the same goes for the minimized variance. because we found, again, no statistical difference between the results. So it means that once you get the shortest equivalent, you don't care too much which generator you use to generate the text. So we were a little bit puzzled by this, but that's what we get from the results of this work. We break down let's say the comments of the evaluators that we got, and as you can see here, we see that most of the times that humans said that the sentences are not comprehensible is because whether they are ambiguous or they are complex. Okay, so this hints at the fact that we should really focus on generating text and improving text based on ambiguity. So we should focus on generating text which cancels out ambiguities, because we can see that it's a real big issue, and people were actually struggling a lot with ambiguity of the text. This is one of the examples that it's clear and were really puzzling for people. So a sentence which is generated is if B is a tetrahedron, then B is a tetrahedron, and it is not the case that C is a tetrahedron. So you can have at least two different interpretations, which is you get the scope of the implication first, and then the conjunction and is the one that links the two parts of the sentence. So you have an implication on the left, conjunction, and a negation on the right. The second interpretation is you get the implication as the main connective of the sentence, and you get the left-hand side, B is a tetrahedron, and the left-hand side of the implication is B is a tetrahedron, and it is not the case that C is a tetrahedron. To understand which is the intended meaning of this original sentence, we had to take a look at the original formula. And as you can see from the original formula, it's very clear that interpretation is number 2, right? Because since logic is formal, you have brackets that tells you the scope of operators. But this does not happen when these formulas are generated in natural language. So when you translate formulas, so a formal language into natural language, you get ambiguities that you do not have in the original formulas. So that's why we really need to focus on how to generate sentences which cancel out or reduce ambiguity. So the main takeaways: manipulating the input improves the sentences, but there is no statistical evidence that the shortest formula is actually the best input, because we saw that there is no statistical difference between the manipulation using the tree and the minimized version of the formula. And based on the results of the human evaluation, we see that there is the need to take measures to mitigate ambiguity. Where do we go from here? So the future work is, first of all, develop an automatic metric, taking into account the logic to text challenges, because we saw that BERT score or semantic-based metrics do not focus exactly on the problems that we are interested in and are not very faithful to score the text that we generate. The same goes for n-gram-based metrics. Then we are thinking of experimenting with neural models, for example, I don't know, using graph neural networks or, I don't know, ChatGPT-like models or whatever. And then extending this minimization algorithm, the one that I worked on in Barcelona, to more expressive logics, because now we were limited to a fragment of logic which was quite easy, so propositional logic, but we wanted to expand this with quantifiers and formulas which are more complicated. So, well, if you're interested, this is a list of references. And so this is the end of the talk, let's say, at least from my side. I can show you now an interactive demo. We can talk together and we can play with this demo together. Unfortunately, as I told you before, I didn't have time to Dockerize it, so you cannot possibly play with it, but you can find it on GitHub and you have to build everything on your own. And also, while we play, you can ask questions and you can give me feedback, which is really much appreciated. Thanks a lot.
Thank you so much. It was pretty dense.
Yeah.
Super interesting. So, do you prefer that we start with some question, or you would like first to show the?
Well, can you see it or no? I think
we can see question time slide.
Yeah. So I will. In the meantime, I will change the screen so that we have the tool ready. And
so I got already one question at least.
Yeah. Go ahead. Can you see? Yes. Okay. You can.
Yes. So, Francesco, maybe no, I don't know. I saw a question. You can unmute yourself or. Okay, no, maybe I saw the wrong emoji. Okay, no.
If you have a question, you go for it. I mean, I'm.
Yeah. Feel free to unmute yourself if you have a question. I will start with one. Yes. Maybe I missed if you said it at the very beginning, but I was wondering if your models, if you also take advantage of pre-trained models of natural language, and because starting from scratch, it's very difficult.
Yeah.
Okay. So yes, of course, but
well, not. I mean, yes, but no. I mean, I understand the question, but so far, no. So far, all the systems that we have used. So Randa, Lola, you saw all these. All of them are rule based. All of them
rule based. Okay.
You see all the trees, all the.
Yeah. Okay.
So I do not take advantage of any neural models so far. So all of the systems that you've seen in this presentation are.
Okay. So future work will be with
exactly.
And I guess with pre-trained models, maybe on general language, that then you can fine tune on logic one. Okay. Because we are doing a challenge where we are also using the same score you mentioned. Obviously, cosine similarity using SBERT and also BERT score to evaluate conversation between chatbots. Okay.
But the thing is, the texting that I am handling, they are, very peculiar. You saw the type, like without adjectives, a lot of negation, and BERT. If BERT misses one of these things, and anyway, it says that the semantic similarity is very high. Indeed, it's not, because if it misses a negation, the meaning of the text changes completely. This is the main problem, the main issue with using this evaluation metrics. But with other tasks, there is no problem, because maybe you don't need these semantic fine-grained nuances that are needed for my task.
Okay, thank you. So you can go on with the demo. I'm curious now.
Yeah. So I mean,
sorry, there is a question from Marco.
Yeah, of course. Hello.
Hi, Eduardo.
Hello.
I have a more practical question. You said at the beginning of the talk that one of the possible use cases of your work would be the one of teaching students in a more, I would say, concrete way. They have a direct translations of very complex logical expression. So I was wondering, have you already tried to use your demo, the demo that you will show us to actual real students, or is it something that you're planning to do in the near future?
Yeah, this is a really good question, actually. So no, this is the first time someone sees this demo, apart from me and a colleague of mine. So you are the first audience of this demo. So it's very limited. The demo that you will see here, it only contains the 3 original systems, so the baseline, Randa, and Lola, but it's already a good one to understand how changing the system actually changes the translation. You see, like if you use a system which is, let's say, baseline, which does a literal translation, against something, some system which does some syntactic optimization versus something else that does logic optimization, you see how the same logical formula is translated into text. So yes, this is something that we plan to do. And when I was in Barcelona, there was a colleague of my supervisor there that was very interested in this. So probably no, maybe next year I will go there again when he's teaching logic to students, and I can show this demo to them. Yes, that's of course it will be improved with the more I don't know, whatever, more functionalities and everything. But yes, that's something that we have thought of, because it's not only something theoretical, like you know, working on things that can improve the knowledge of NLP or computational linguistics or linguistics, but also something that can have a practical application.
Okay, thank you very much.
Thanks.
I remember that when I was a first-year university student, I was really struggling in Calculus 1 with logic. So if I would have access with to tools like that and to a tool like that, it would have been a real pleasure to use it. So good job and keep up the work.
Thank you so much. Hopefully I can help people.
Go ahead, Vish.
Yeah, it takes some time to take it down. Thank you, Marco, for that question. I had a same question and also comment. You see a lot, chain of thought prompting is quite popular with ChatGPT kind of models. And I remember like 2 years ago as a student as well, I was really struggling with solving those problems from a book. Especially there's one called the 3 God problem, very famous. So the thing about logic problems is you have a lot of statements that come, in order. So have you thought of, how you can actually break down multiple statements that actually lead to solving a problem?
Yeah. Also, this one is a really good question. The thing is, for now, we have focused on single statements. So the input that you get from the inputs that these systems get are just one formula. So we do not have several statements. They wouldn't be able to handle anything which is not a single formula. And again, as I said before at the beginning, since they are rule-based, the domain in which they can work on it's very, very limited, right? But this is for sure something that we will explore using. I've taken a look already at chain of thoughts prompts like this, and it's something that we will want to explore in the future. Definitely, yes. And also, from the other perspective, from the text perspective, you get the same problem. Because, for example, you can have one single formula, which is very long, which is translated into one single sentence, which is very long and extremely disfluent, but you may want to split it. Of course, these rule-based systems are not very good at doing it. It's very complicated to do it with rule-based systems. But neural language models are good at, let's say, I don't know, dividing, splitting, merging, applying these linguistic operations on text. So good questions, and there is both aspects of the coin. Yeah, both sides of the coin. Yeah.
Yeah. Thank you.
Thanks. So I can, in the meanwhile, while people think of questions, I can show something. So, for example, this is an easy formula, which is not large A. Here there are the 3 modes that I presented in the works. So this, if you select this one, it's a literal translation of the formula, and what you get is it is not the case that, because negation is translated as it is not the case, that it is not the case that A is large, which is very disfluent, and people would say, oh my God, this is a disaster, please do something. Then, if you go with a syntactic optimization of this formula, which is run the system, what you get is the first one, it's kept still. It is not the case that. But the second one, the second negation, is injected inside. So you perform a negation directly, syntactically, inside the verb phrase. So you put the negation inside, and you get it is not the case that A is not large. But the best translation of this formula is, of course, when you remove the two negations, because they are logically redundant, and you get something of the shape like this. So you remove the two negations, A is large, which has the same meaning as negation, negation, A is large. So that's the demo. I mean, of course, this demo works with also formulas which are much more complex, but only with a specific limited, let's say, lexicon, because it's the one that we implemented in this rule-based system. And that's, you know, the limitations of rule-based systems. And the other limitations that these systems have is if their formula is longer than, I don't know, 100 characters, it crashes, because again, they are not robust enough to handle all possible types of input. Yes, maybe we can I don't know, try with let's see.
Okay.
Maybe we can try with one of the formulas that I have on the. Let me see. I can show you something which is more interesting than just, for example, yeah, this one. Let's see if this one works. This one should work. So it's, let me see. I think I can copy paste it from here. Is there a question, maybe? No?
Yeah, in the chat.
In the chat, okay.
Yeah.
Can you read it for me in the meanwhile?
Yeah. Can your approach be used for breaking down statements from a language like Prolog directly?
Mm-hmm. Yeah, I see the question. It's I think it's very linked to what Vij said. So
yeah, the question is from Vij.
yeah. I mean, no. These systems, no. But the approach theoretically could. There are other things in the literature that have tried to do it. Even from probably, you know, these data sets like math 2, math 3, 4, 3, this kind of, you know, and based on the international mathematics Olympiads, this kind of stuff. And they tried with POLM, I guess, Codex, you know, large language models. They can do it, but again, of course, they are not perfect. So I think that when working with large language models, when you try to something that I think that should be really, really important when working with large language models is a neural symbolic approach. So you get large language models with something else, which, I don't know, knowledge base, or I don't know, logic system, or whatever, that can help with the faithful part of the thing. Because with large language models, again, you can create, you can manipulate things much more in an easier way. But the logic system, they are very much you know, flawed under this point of view. So combining the two aspects, having something that can handle both the logic side, so what you say, and the linguistic part, to have something which is more fluent and comprehensible, that would be the best thing. So fast forward to probably next year, I will go to Aberdeen in Scotland for another internship, and I will work there in a company which is focused on creating generators. So I might want to focus on something which is neural symbolic.
Okay. So I also shared in the chat your Twitter. So if anybody else has any question, curiosity, whatever to ask to Edo, he will reply. I
Definitely.
check the messages on Twitter.
Definitely, I'm always available for any question, feedback, whatever you might think of. I really like talking to people.
Okay. Perfect. So thank you again. And now we reached the final, let's say, time schedule on the calendar. Thank you again. It was super interesting, and hope to see you soon.
Thanks a lot. Definitely, I thank you so much for the opportunity, and really, it was a pleasure. I hope you enjoyed it, and whenever you want to reach me, just don't hesitate. I will respond. Yeah.
Okay. Thank you, Edu, again. Thank you to everybody, and see you at the next Tech Talk. Bye-bye.
Bye-bye. Bye, everybody.
Bye-bye.